Hello, in today's podcast, we're going to look at what remains after a star has died. What happens to the cores, the leftover cores of dead stars? Well, to remind you, one of the key concepts when we're talking about stars is that of hydrostatic equilibrium. In a functioning star, by which I mean one that's still undergoing nuclear fusion in the core, the gravity that's trying to pull it all together is counterbalanced by the gas pressure or thermal radiation pressure, which gives it equilibrium. And over the lifetime of the star, stars change shape many times because of changes in that equilibrium. The thermal radiation pressure either gets bigger, which pushes out the star until the equilibrium is restored, or it gets weaker, in which case the core collapses until equilibrium is restored. So that's in a normal star. Now, we've previously met white dwarfs. White dwarfs happen when low or intermediate mass stars, up to about 8 solar masses, reach the end of their lifespan. In these cases, the core is no longer generating new power, new energy through nuclear fusion. The white dwarf is still hot, very hot. It's losing energy by radiation, but it's collapsed. And there's no longer the thermal pressure there, so what's creating the equilibrium? Well, it's electrons. In any case, any type of weird type of matter where by the extreme gravity it's pushed in together, we call that degenerate matter. And this nature of matter, electron degenerate matter, the atoms still exist, the nuclei still exist as nuclei, but the electrons that surround them are forced into their lower energy states, and you can imagine them moving around and pushing back out at each other, and actually doing so at a significant fraction of the speed of light. And it's that force of them pushing back at each other which is resisting gravity, which is maintaining the size of the white dwarf. So that size is about the size of our Earth for a core remnant of solar mass. The composition depends on the final product of the nuclear fusions. So for low mass stars, it's probably carbon oxygen. For intermediate mass stars, it's probably oxygen, neon, and magnesium. Interestingly, the mass of a white dwarf determines its radius. You might expect that, but it's actually an inverse relationship because the electron degeneracy pressure is kind of fixed. It can't get bigger or smaller. So the only variable that can really change is the mass. And the more mass, the more gravity, so it collapses the star, the remaining white dwarf, further and further. That actually means that there's a limit. You cannot get a white dwarf greater than about 1.4 solar masses. This is called the Chandrasekhar limit. Remember, that's not the mass of the star that created the white dwarf. A large amount of that mass will have been blown away during the red giant and asymptotic red giant phases, but it is the mass of the remaining core. So that remaining core mass cannot be greater than 1.4 solar masses. And as you approach that limit, white dwarfs actually get very small indeed. So what happens if, as a result of a very large star, greater than 8 solar masses exploding, probably in a supernova, what do you get then? Well, you can't have a white dwarf because the electrons, they can't produce enough force to resist the gravity. Instead, the electrons get pushed into the protons, which leaves behind the neutrons in a kind of weird superfluid with actually an iron crust around the outside. Now, the neutron degeneracy pressure, which is basically the neutrons pushing against each other, you've eliminated all of the empty space that we expect to see inside an atom. That 5 orders of magnitude between the size of an atom and the size of a nucleus no longer exists. That means you're a neutron star which has a mass of about 10 to the 15 kilometers. And it doesn't actually depend what the mass of a neutron star is, although it's a relatively limited range. It can only exist between about 1.45, the Chandrasekhar limit, and about 3 solar masses, the Oppenheimer-Volkoff limit. This means the density of a neutron star is about 10 to the 17 kilograms per meter cubed, and its escape velocity is about 0.7 c. That has really weird effects if you could look at a neutron star. For example, you could see more than half the surface at any one time. So that 10-15 kilometers is illustrated here against the size of Manhattan. You may or may not be familiar with Manhattan, so here it is approximately centered on the school compared to Suzhou and the surrounding areas. So the Oppenheimer-Volkoff limit is about 3 solar masses. If your stellar remnant has a mass of greater than 3 solar masses, then even neutron degeneracy pressure is not going to do the job. But before we get onto that, pulsars. Some neutron stars spin very, very rapidly by conservation of angular momentum, and in combination with the very strong magnetic fields that spin round, that means that their radiation often goes off like lighthouse beams from the magnetic poles. These were first observed as radio pulses by Jocelyn Bell in the 1960s, which didn't get her a Nobel Prize, compared to Penzias and Wilson, who you'll meet later, and her supervisor, who both did. But she was working at Cambridge University in the radio astronomy, and they detected a beep, 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 well, actually about 30 pulses a second, but faster than that. And for a while, they thought it might be aliens. They couldn't think of anything that would produce regular pulses like this until this mechanism was realized. So many neutron stars that we know as pulsars, pulsating stars. As I was saying, if you exceed the Oppenheimer-Volkoff limit, then neutron degeneracy pressure is no longer enough and your neutrons are crushed into nothingness. The star collapses to form a singularity. A singularity is a point of 0 size, 0 volume, and infinite density. The singularity is the heart of a black hole, but what surrounds the singularity, the black hole itself, does have a defined size, and we define it by something called the Schwarzschild radius, which only applies to non-rotating black holes, which is not very realistic, but the Kerr radius, the rotating version, isn't that much different. At the edge of a black hole, at the Schwarzschild radius, you have the event horizon. Anything within the event horizon has an escape velocity greater than the speed of light. Anything within the event horizon can no longer escape. Anything outside the event horizon theoretically can, although close to the event horizon, it would have to be traveling at a very significant fraction of the speed of light. Okay, so how do we detect black holes if they can't emit anything? Well, a couple of things. One, according to quantum physics, we have this thing called pair production, where pairs of virtual particles are created in space all the time. Right at the event horizon, one of this pair could be pulled into the black hole, leaving the other part both real, no longer virtual, and able to escape. That's called Hawking radiation, and it means that they do give off some radiation and at the same time very slowly evaporate. But we haven't actually detected that yet. Also, if your black hole is nearby other objects, for example, here in this photograph, it's nearby a companion star, and it's pulling material from that object. As that material falls into the black hole, it gets very, very heated, and therefore gives off X-rays and other types of radiation. And these we have detected, and it's not the only possible explanation, but certainly probably the best explanation for their existence is black holes. And thirdly, if you put 2 black holes and have them rotating nearby each other, which is rare, but it does happen, then they give off significantly sized gravity waves. And as of January 26, for the first time, we detected the gravity waves that result from a pair of black holes approaching and then colliding with each other, which produced a very big explosion. Okay, so that concludes our look at stellar evolution. Thank you very much. Oh, sorry, one final slide. Here's another artist impression of near a black hole, and you can see the very strong gravitational effects distorting the star field behind. Okay, that really is the end. Thank you very much.